Tonight, we're going to talk about a wall you can't see, touch, or cross. It has no surface, no substance, no physical presence at all. But it is the most fundamental boundary in existence. And everything you will ever know, everything any telescope will ever observe exists on your side of it. And here's what's going to change your understanding of where you actually are. The universe is not infinite to you. It's a bubble, a sphere with you at the center, surrounded by a horizon you can never reach. And beyond that horizon, there are places filled with galaxies and stars and possibly life that are permanently, irreversibly cut off from us. Not because our rockets aren't fast enough or because we haven't invented the right technology yet, but because of physics. And that wall has been quietly moving our entire lives, swallowing galaxies we can still see tonight, turning them from places we might one day reach into places we never will, without a single sign that it's even happening. By the end of tonight, you're going to understand what that barrier is, why it exists, why it's growing, and why the universe you can see is only a small fraction of the universe that actually exists. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Start with something simple. Standing on a beach, looking out at the ocean, there's a point where the water seems to disappear. The horizon. The ocean keeps going past that point. Ships vanish over it and reappear later. The horizon isn't an edge of the ocean. It's just the limit of what your eyes standing at your particular height can physically see because the surface of the earth curves away beneath the water. Walk to a hill, climb higher, and the horizon moves outward. You see farther. The ocean itself never changed. Only your ability to see across it changed. Now take that idea and scale it up to the entire universe. There is a horizon out there too, but it isn't caused by curvature and it isn't something you can simply climb a hill to see past. It's caused by something built into the fabric of the universe itself. And no amount of climbing, no amount of technology, no amount of patience will ever let you see past it. That's the barrier we're talking about tonight. In the 1700s and 1800s, several astronomers noticed something that seemed like it shouldn't be true. If the universe were infinite, filled evenly with stars in every direction, then no matter which direction you looked, your line of sight should eventually hit a star. Every single point in the sky should be blazing with starlight, layered upon layer, stretching back forever. The night sky should be as bright as the surface of a star, not dark at all. But it isn't. The sky at night is mostly dark with scattered points of light. This became known as a paradox, named after the German astronomer who wrote about it extensively, though others had noticed the problem earlier. For a long time, nobody had a fully satisfying explanation. Some suggested dust in space blocked distant starlight. But that explanation doesn't actually work because dust would eventually heat up and glow just as brightly as the stars it absorbed. The real explanation didn't arrive until the 20th century, and it turned out to be deeply connected to everything we're discussing tonight. The universe has a finite age. Light from stars and galaxies far enough away simply hasn't had time to reach us yet. And on top of that, the universe is expanding, stretching the light from the most distant sources into wavelengths too long for your eyes to detect as visible light at all. The darkness of the night sky isn't a lack of stars out there. It's a direct, visible consequence of the same finite speed of light and the same cosmic expansion that create the barrier we're building toward. The night sky has been quietly hinting at this boundary for as long as humans have looked up and wondered why it wasn't simply full of light. The first thing you need to understand is that light doesn't travel instantly. It moves fast, about 186,000 miles every single second. But that speed is still finite. It still takes time to go from one place to another. When you look at the sun, you're not seeing it as it is right now. You're seeing it as it was about 8 minutes ago because that's how long its light takes to cross the 93 million miles between the sun and the Earth. Look at Sagittarius A, the supermassive black hole sitting at the center of the Milky Way, and you're seeing light that left there about 26,000 years ago. Look at the Andromeda Galaxy, our nearest large galactic neighbor, and you're seeing light that departed roughly 2.5 million years ago, long before modern humans existed. Every single thing you see in the night sky is a message from the past. Some of those messages are minutes old. Some are millions of years old. Some are billions of years old. You are never looking at the universe as it is. You are looking at layers upon layers of history stacked on top of each other, all arriving at your eyes at the exact same moment. This alone should feel strange. There's an even deeper layer to this, something that goes beyond simply saying light takes time to arrive. Relativity tells us that the very idea of right now, applied to something happening billions of light years away, doesn't actually mean what it seems to mean. Simultaneity, the notion that two distant events happen at the same moment, turns out to depend on the observer and on how that observer is moving in ways that only become noticeable across enormous distances or extreme speeds. There is no single universal objective now that applies equally to us and to a galaxy billions of light years away in the simple intuitive sense you might expect. Asking what is happening on a distant galaxy right now is, in a strict physical sense, a question without a perfectly well-defined answer, because different observers moving differently through spacetime would reasonably disagree about which distant events count as simultaneous with this exact moment here on Earth. This doesn't change any of the physics we're about to describe. The cosmological event horizon still functions exactly the way we're going to explain it. But this reveals that the barrier we're building toward isn't just a limitation on what we can see. It touches something even stranger about what the words here and now even mean once you're talking about distances this large. But it gets stranger because the simple fact that light takes time to travel is the seed of the entire barrier we're building toward tonight. The universe itself has an age. Based on the best current measurements, it's approximately 13.8 billion years old. That means light has only had 13.8 billion years to travel since the earliest moments after the beginning of everything. So, you might think reasonably that the farthest anything could be from us is 13.8 billion light years away, since that's as far as light could have traveled in the time the universe has existed. That would make sense in a universe that wasn't doing anything strange. But our universe is doing something very strange. It's expanding. And that expansion changes everything about how far we can actually see and how far away things actually are right now. Here's the analogy that actually works. And it's one used by physicists for almost a century now because nothing better has ever been found. Take a balloon and draw a few dots on its surface with a marker spaced out randomly. Now start inflating the balloon. Watch what happens to the dots. They all move away from each other. Every dot sees every other dot receding. There's no center to this expansion on the surface of the balloon. No dot is the special one that everything is expanding away from. They're all moving apart from each other simultaneously because the surface itself, the space between the dots, is stretching. This is roughly what's happening to the universe, except in 3 dimensions instead of 2 and without any center at all. Galaxies aren't flying through space away from us like debris from an explosion. Space itself, the fabric between galaxies, is stretching, carrying galaxies along with it. This distinction matters enormously, and it's the key to understanding the barrier. Because when space itself stretches, there's no upper limit on how fast 2 points can appear to move apart from each other. Even though nothing is actually moving through space faster than light, the speed limit of light applies to things moving through space. It doesn't apply to space itself stretching. This one distinction is going to explain almost everything else we talk about tonight. While we're here, let's clear up a common misconception, one that trips up even people who've read a fair amount about cosmology casually. The beginning of the universe is often described using the term Big Bang, and that phrase naturally conjures an image of an explosion, a single point in space where everything detonated outward into a pre-existing empty void. That picture is wrong in an important way. There was no pre-existing empty space for anything to explode into. Space itself, all of it everywhere, began stretching from that initial moment. Every point in the current universe, including the point where you're sitting right now, was in some meaningful sense present at the very beginning. Because space itself has been continuously stretching outward from every point simultaneously ever since, with no special point that everything is expanding away from. There's no location you could travel to that would put you closer to where the Big Bang happened, because it didn't happen at a location. It happened everywhere all at once, and it's still happening in the sense that the same stretching of space that began then is the same stretching of space carrying galaxies apart from each other today, including the stretching responsible for the barrier we're describing. This is genuinely difficult to picture intuitively because everyday experience only gives us examples of explosions happening at a location within pre-existing space. The balloon analogy helps here. Again, there's no special dot on the surface of the balloon that the inflation started from. Every dot moves away from every other dot uniformly because the entire surface is stretching everywhere at once. The Big Bang wasn't an explosion in space. It was the beginning of space itself stretching everywhere simultaneously. And that stretching never actually stopped. It only changed over time, briefly slowing during periods when gravity from all the matter in the universe had more influence, and then roughly 5 billion years ago, beginning to accelerate again as dark energy took over as the dominant influence on the large-scale behavior of the cosmos. In the 1920s, an astronomer named Edwin Hubble made an observation that changed everything. He found that distant galaxies weren't just moving away from us. The farther away a galaxy was, the faster it appeared to be receding. This became known as Hubble's law, and it's remarkably simple in its basic form. Recession velocity increases proportionally with distance. A galaxy twice as far away recedes about twice as fast. A galaxy 10 times as far away recedes about 10 times as fast. This relationship holds up remarkably well across enormous ranges of distance. And it's one of the most solid, well-tested relationships in all of astronomy. Here's how astronomers actually measure these staggering distances with any confidence. And it's a clever piece of detective work on its own. You can't stretch a tape measure to another galaxy. Instead, astronomers rely on objects called standard candles, objects whose true brightness is known in advance for reasons rooted in the physics of how they work. A type Ia supernova, the explosive death of a certain kind of white dwarf star, always detonates in almost exactly the same way because it happens when the white dwarf accumulates mass from a companion star up to a very specific, well-defined physical limit, at which point it explodes with almost exactly the same total energy output every single time, regardless of which galaxy it happens in. Knowing the true brightness of the explosion and comparing it to how bright it actually appears from Earth lets astronomers calculate precisely how far away it must be, using the simple, well-understood way that light dims with distance. A candle that appears dim is either weak or far away. Knowing the candle isn't weak because you know its true brightness in advance tells you it must be far away, and by exactly how much. This technique, applied to thousands of these stellar explosions across a huge range of distances, is what allowed astronomers in the 1990s to build a reliable distance ladder stretching billions of light years into the past. And it's what revealed, unexpectedly, that the most distant supernovae appeared dimmer than expected if the universe were merely coasting along at a constant expansion rate. They were farther away than a non-accelerating universe would predict. That single unexpected dimness, observed by two independent research teams working separately, is the entire observational foundation for everything we now understand about accelerating expansion. And therefore, for the entire concept of the barrier we're discussing tonight. It's fair to ask how confident we should be in all of this, given how strange the conclusion is, and good science should be able to answer that kind of skepticism. Honestly, over the decades, alternative explanations for redshift have been proposed and tested, including an idea sometimes called tired light, which suggested that light might simply lose energy gradually as it travels enormous distances for reasons unrelated to any expansion of space at all, mimicking the appearance of redshift without any actual stretching occurring. This idea has been tested against multiple independent lines of evidence, including detailed patterns in how distant supernovae brighten and fade over time, patterns that would be stretched out in a specific predictable way if expansion were real, and patterns that tired light models fail to reproduce correctly. The evidence for genuine cosmic expansion, rather than some alternative explanation for redshift, now comes from several completely independent directions. The supernova brightness measurements we just described, detailed structure within the cosmic microwave background, the observed relationship between galaxy clustering patterns and distance, and the measured abundance of light elements like hydrogen and helium produced in the earliest minutes of the universe. All of which agree with each other to a remarkable degree when interpreted through the framework of an expanding universe with accelerating dark energy. This kind of agreement across independent, unrelated methods is exactly what gives scientists confidence in a conclusion, even one as strange-sounding as space itself stretching, carrying galaxies away faster than light. The barrier we're describing tonight isn't a fringe idea or a single controversial measurement. It's the settled conclusion of overlapping, independently verified evidence refined and cross-checked for more than 2 decades. The rate of this increase is called the Hubble constant, and current measurements put it at roughly 43 miles per second of additional recession velocity for every 3.26 million light-years of additional distance. That number might sound small for nearby galaxies. It is small. Andromeda, our closest large neighbor, is actually moving toward us due to gravity, not away, because at that distance, gravity between our 2 galaxies overwhelms the effect of cosmic expansion entirely. But keep applying that relationship outward to greater and greater distances and something remarkable happens. Eventually, you reach a distance where the recession velocity driven purely by the stretching of space itself equals the speed of light. Go beyond that distance and the recession velocity exceeds the speed of light. This isn't a violation of relativity. Nothing is moving through space faster than light. The space between us and that galaxy is simply stretching fast enough that the distance itself is growing faster than light could ever cross it. This distance, where recession velocity equals the speed of light, has a name. It's called the Hubble radius or sometimes the Hubble sphere. Based on current measurements, it sits at roughly 14.4 billion light-years from us. Anything beyond that distance is receding from us faster than light can travel. Now, here's where it gets genuinely difficult to wrap your mind around. So, slow down for a moment. A galaxy beyond the Hubble radius receding faster than light can still have its light reach us under certain conditions, because the space between us and it might have been expanding more slowly in the past, allowing photons to make progress, and because the expansion rate itself isn't perfectly uniform across all of cosmic history. Light emitted from a galaxy long ago, when that galaxy was closer and the expansion rate different, can still eventually work its way to us, even if that same galaxy is now receding faster than light due to its current much greater distance. This is part of why the true edge of what we can ever observe isn't simply defined by the Hubble radius alone. There's a more precise concept, and it's the one that actually defines the true permanent barrier. It's called the cosmological event horizon. Think of it this way. The observable universe, the part we can currently see, is defined by how far light has managed to travel to reach us since the beginning of everything. Right now, that observable universe has a radius of about 46 billion light-years. Notice that number is larger than the age of the universe in years, 13.8 billion. That seems impossible at first, like it breaks the speed of light. It doesn't, because that 46 billion light-year figure isn't the distance light has traveled. It's the current distance to the point that light left billions of years ago. The galaxy that emitted that light was much closer to us when it did so. But in the time that light spent traveling toward us, space itself kept stretching, carrying that galaxy's current position much farther away than it was when the light departed. So the light took 13.8 billion years to arrive. But the source of that light is now, right this moment, about 46 billion light-years away because the universe kept expanding the entire time the light was in transit. This is the observable universe. Everything within that 46 billion light-year radius is something whose light has had time to reach us. But the observable universe is not the same thing as the entire universe. The entire universe might be far larger, possibly infinite. We genuinely don't know. What we do know is that there's a portion of it we can see and a portion we can't. And the line between those two portions is the first version of our barrier.it helps to make this concrete with real examples because 46 billion light-years is an abstract number until you attach actual galaxies to it. Astronomers measure distance to faraway galaxies using something called redshift, which is really just the balloon analogy again applied to light itself. As space stretches between us and a distant galaxy, the light traveling through that stretching space gets stretched too, shifted toward longer, redder wavelengths. The more the light has been stretched, the higher the redshift and the more distant and the older that light turns out to be. In 2016, astronomers identified a galaxy called GNZ11 with a redshift high enough to place it at a look-back time of about 13.4 billion years, meaning its light left when the universe was only about 400 million years old. More recently, observations from newer space telescopes have pushed even further, identifying candidate galaxies with light dating back to within roughly 300 million years of the beginning of everything. Reaching these extraordinary distances required a specific kind of technological leap because the light from these earliest galaxies has been stretched so dramatically by cosmic expansion over billions of years, it no longer arrives as visible light at all. It arrives as infrared radiation, wavelengths longer than what human eyes can detect. And this is precisely why a space telescope like the James Webb Space Telescope, launched in December of 2021 and designed specifically to observe in infrared wavelengths, was able to detect galaxies that earlier telescopes built primarily to observe visible light simply could not see at all, no matter how long they stared at the same patch of sky. Earlier telescopes weren't failing due to insufficient magnification. They were looking for the wrong kind of light entirely because the light they needed to detect had already been stretched by billions of years of cosmic expansion into wavelengths their instruments weren't built to see. Every major leap in how far back we can observe has come from building instruments tuned to increasingly longer wavelengths, chasing the ever-reddening light of the most ancient, most distant galaxies as expansion stretches it further and further from the visible spectrum. This pattern will likely continue. Future instruments tuned to even longer wavelengths may eventually push our view back closer still to that 380,000-year mark, the very edge where light itself began. These galaxies existed in what's sometimes called the cosmic dawn, the era when the first stars and galaxies were forming out of primordial gas. Their light has been traveling toward us for almost the entire history of the universe. And because of the expansion that occurred during all that travel time, those galaxies, assuming they still exist in some form, would now be roughly 30 billion light-years away or more, even though the light we're seeing left when they were far closer. This is the observable universe at its absolute limit, the oldest, most distant light we can currently detect with any instrument. There's another class of object that played a huge role in mapping these enormous distances long before the most distant galaxies were detectable at all. Quasars are among the most luminous objects in the entire universe, powered by supermassive black holes actively consuming enormous amounts of surrounding gas and dust, generating more light than an entire galaxy of ordinary stars combined, all from a region not much larger than our solar system. Because they're so extraordinarily bright, quasars remain detectable across billions of light-years, even when the ordinary galaxies hosting them would be far too faint to see directly. Some of the most distant known quasars have redshifts placing them at look-back times of over 13 billion years, meaning we're seeing supermassive black holes that had already grown to billions of times the mass of the Sun when the universe was less than 1 billion years old. A fact that itself remains a genuinely puzzling open question in astrophysics. Since building a black hole that massive that quickly is difficult to explain with standard models of black hole growth. These distant quasars serve as some of our most reliable markers for calibrating the true scale of the observable universe, bright beacons scattered across billions of years of cosmic history, each one a data point helping refine exactly how far and how fast everything out there truly is. Reaching these extreme distances at all depends partly on a genuinely elegant trick nature provides for free called gravitational lensing. Massive objects like entire galaxy clusters bend the fabric of space-time around them enough to visibly distort and magnify the light passing near them, the same way a lens made of glass bends light in a camera or a telescope. When a massive foreground cluster happens to sit directly between us and a much more distant, much fainter galaxy, the light from that distant galaxy gets stretched, magnified, and sometimes duplicated into multiple images, arriving brighter and larger than it would have otherwise appeared. Astronomers actively search for these natural cosmic lenses and use them deliberately, essentially borrowing the gravitational field of an entire galaxy cluster as a second telescope lens layered in front of our actual instruments to detect galaxies that would otherwise be far too faint to see at all. Some of the most distant, faintest galaxies ever detected were only visible because a massive foreground cluster happened to be positioned perfectly to magnify their light on its way to us. Without that gravitational assistance, they would have remained completely invisible, hidden not by the barrier we're describing tonight, but simply by their own extreme faintness at such enormous distances. It's a reminder that even within our own observable universe, at its faintest, most distant edges, we're often relying on the universe's own gravity to help us see as far as we possibly can, right up to the true limits that light and time allow. But even that isn't quite the true edge of what light can tell us, because there's an earlier barrier, one that exists in time rather than distance. For roughly the first 380,000 years after the beginning of everything, the universe was too hot and too dense for atoms to form. Matter existed as a hot, opaque plasma, a soup of charged particles, electrons and protons unable to combine into stable atoms. Light couldn't travel freely through this plasma. It scattered constantly off free electrons. The same way light scatters inside a thick fog, unable to travel in a straight line for any meaningful distance. The universe in its earliest phase was genuinely opaque, like being inside a cloud so dense you can't see your own hand. Then, roughly 380,000 years in, the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms in an event cosmologists call recombination. Once that happened, the fog lifted. Light could finally travel freely in straight lines for the first time in cosmic history. That first light released the moment the universe became transparent is still traveling today. We can detect it faintly, uniformly in every direction we look, and it's called the cosmic microwave background. It's the oldest light in the entire universe, and it represents an absolute wall for anything based on visible light or its relatives. We cannot see any further back in time using light, ever, no matter how good our telescopes become, because before that moment there simply was no light traveling freely for us to detect. There's a fascinating detail buried inside the cosmic microwave background, one that reveals something about our own motion through the universe. The CMB is remarkably uniform in every direction, but not perfectly. It's very slightly warmer in one direction of the sky and very slightly cooler in the opposite direction, a pattern called the CMB dipole. This isn't a feature of the early universe itself. It's caused by our own motion, the motion of our galaxy, our local group, and everything gravitationally bound to us moving through space relative to the average rest frame defined by the background radiation itself. Measuring this slight temperature difference lets astronomers calculate our actual speed relative to this cosmic rest frame. And the answer is that we're moving at roughly 1,340,000 miles per hour relative to it, a combination of the Sun's orbit around the Milky Way's motion within the local group, and the local group's overall motion toward that great attractor we mentioned earlier. It's a strange thing to realize. Even standing still, reading or listening to this, you're moving through the universe at a staggering speed relative to the oldest light in existence, carried along by the combined gravitational dance of our galaxy and everything pulling on it. None of this motion helps us outrun the barrier we're describing tonight, since it's utterly negligible compared to the speed of light. But it's a small, humbling reminder that nothing in the universe, including us, is ever truly standing still. This is a second kind of barrier, different from the cosmological event horizon we're building toward. And it shows that even looking backward in time, not just outward in space, has its own hard limit. There are theoretical ways around this particular barrier, at least in principle. Neutrinos, ghostly particles that interact with matter extremely rarely, could in theory carry information from moments even earlier than recombination, since they decoupled from the hot plasma much sooner than light did. Gravitational waves, ripples in spacetime itself, could in theory carry signals from even earlier still, potentially from fractions of a second after the beginning of everything. Detecting either of these primordial signals remains far beyond current technology, but it isn't forbidden by physics the way crossing the cosmological event horizon is. That distinction matters. Some barriers are barriers of current technology, waiting for a clever enough instrument. Others are barriers of pure physics, waiting for nothing, because no instrument, however clever, could ever get around them. The cosmic microwave background is closer to the first kind. The cosmological event horizon is the second kind, and it's the one we're really here to talk about tonight. But here's the part that turns this from merely fascinating into something closer to unsettling. That barrier isn't fixed. It isn't a permanent boundary sitting at 46 billion light-years forever. It's changing actively right now as you listen to this. And it's changing because of something discovered in the late 1990s that reshaped cosmology almost overnight. In 1998, two independent teams of astronomers studying distant exploding stars called Type Ia supernovae made a discovery that stunned the entire field. They expected to find that the expansion of the universe was slowing down over time, the way you'd expect gravity to gradually pull everything back together and decelerate the expansion from the beginning of everything. Instead, they found the opposite. The expansion of the universe is speeding up, not slowing down, accelerating. Something is pushing space apart faster and faster, overpowering the gravitational pull of all the matter in the universe combined. We call this mysterious force dark energy, though the name is really just a placeholder for something we don't fully understand yet. We know it exists because of overwhelming, consistent observational evidence across multiple independent lines of research. We don't know what it actually is. Current estimates suggest dark energy makes up roughly 68% of all the energy content of the universe, dwarfing ordinary matter, which makes up only about 5%, with the remainder in the form of dark matter, which is a separate mystery entirely. Whatever dark energy is, its effect is unmistakable. It's causing the expansion of the universe to accelerate. And that acceleration is the reason our barrier isn't static. It's the reason it's closing in. Here's what accelerating expansion actually means for the boundary of what we can observe. And it's the single most important idea in this entire video. If expansion were constant or slowing down, then over time more and more light from distant regions would eventually catch up to us. Our observable universe would keep growing, slowly, revealing more and more of what's out there forever. But because expansion is accelerating, the opposite is happening in a very specific, very important sense. Galaxies that are currently within our observable universe, galaxies whose light currently reaches us, are being carried away from us at an ever-increasing rate. Eventually, for each of these galaxies, the rate at which space is stretching between us and them will exceed the speed at which their light can make progress toward us. When that happens, the light they emit after that point will never reach us. Not eventually, not after some longer wait. Never under any circumstances for the rest of time. That galaxy doesn't disappear. It doesn't stop existing. It simply crosses a threshold where any information it produces afterward becomes permanently unreachable to us, sealed away behind an ever-tightening curtain caused by the accelerating stretch of space itself. This threshold, the true final boundary beyond which nothing can ever reach us again, is the cosmological event horizon. And unlike the Hubble radius, this one is permanent in its effect. Once a galaxy crosses it, that's it. The connection is severed forever. Let's be precise about the different kinds of boundaries we've now introduced, because cosmologists actually distinguish between several related but distinct concepts, and keeping them straight clarifies exactly what we mean by the barrier. The observable universe is everything whose past light has managed to reach us by now. That 46 billion light-year sphere we described earlier is entirely a statement about the past. The cosmological event horizon is about the future, the boundary beyond which anything happening from this moment forward will never reach us, no matter how long we wait. There's a third related idea sometimes called the effectable universe or the reachable universe, which describes the maximum region we could ever influence if we sent a signal or a spacecraft outward right now at the speed of light starting today. Because of the same accelerating expansion, this effectable region is actually smaller than the cosmological event horizon itself, since anything we send has to contend with the stretching of space during its entire outbound journey, not just at the moment of departure. Current estimates place this effectable boundary at somewhere around 16 to 18 billion light-years, roughly comparable to and closely tied to the event horizon distance, though the precise relationship between these figures depends on the details of how expansion behaves between now and the distant future. 3 different boundaries, 3 different meanings: what we've seen, what we'll ever see, what we could ever possibly touch. It helps to make the effectable universe concrete with a simple thought experiment. Imagine sending a radio signal outward tonight in every direction at the speed of light, the fastest anything can possibly travel. For nearby stars, within a few dozen or a few hundred light-years, that signal would arrive in a perfectly ordinary, calculable amount of time, no different from how you'd expect distance and speed to work in everyday life. For a galaxy a few billion light-years away, the signal would still arrive eventually, but the journey would take billions of years, and the space it traveled through would have continued stretching throughout the entire trip, meaning the actual path length covered would be considerably longer than the distance to that galaxy as it existed on the night you sent the signal. But send that same signal toward a galaxy already beyond the cosmological event horizon and something different happens. The signal leaves Earth at the speed of light exactly as expected, but the space ahead of it keeps stretching faster than the signal itself can travel, meaning the total distance remaining between the signal and its target actually increases over time rather than decreasing. Despite the signal moving as fast as anything in the universe possibly can, the signal isn't too slow. There simply isn't a version of fast enough for that particular destination under the physics we currently understand. It's the clearest, simplest way to state the entire barrier in one sentence. Beyond a certain point, sending your absolute best effort at the maximum speed the universe allows still isn't enough because the target is retreating faster than your best effort can possibly close the gap. All three are finite. All three are smaller than the true total universe, whatever that turns out to be. And all three point toward the same underlying truth, that we are enclosed in every meaningful direction, past, future, and influence, by boundaries carved directly into the geometry of an accelerating cosmos. There's a striking parallel here, one that connects this cosmic scale barrier to something much smaller and much more famous. The event horizon of a black hole, like Sagittarius A*, sitting at the center of our own galaxy. Both are called event horizons for the same underlying reason. And the similarity isn't just a coincidence of naming. Near a black hole, space-time itself becomes so warped that nothing, not even light, can escape from within a certain radius, called the event horizon of the black hole. If you watched a spacecraft falling toward a black hole from a safe distance, something strange would happen as it approached that boundary. You would never actually see it cross. Instead, the light coming from the spacecraft would appear to slow down more and more, stretching toward longer and longer wavelengths, dimmer and dimmer, approaching the horizon in an infinitely slow asymptotic crawl. From your point of view, even though from the spacecraft's own point of view, it would cross the horizon in a perfectly ordinary finite amount of time. This is exactly, mathematically, what happens to a galaxy approaching our cosmological event horizon. Viewed from our perspective, we would never actually witness a galaxy abruptly vanish the moment it crosses. Instead, we'd see its light growing redder and redder, stretched further and further by the accelerating expansion, its apparent passage of time appearing to slow down, dimmer and dimmer, fading asymptotically toward invisibility without ever quite delivering a clean final observable moment of disappearance. In practice, after enough time, the light becomes too redshifted and too faint to detect with any instrument. And for all practical purposes, the galaxy is gone. But mathematically, in the idealized picture, it never quite finishes vanishing from our point of view. The same way an object falling into a black hole never quite finishes falling, from the perspective of someone watching from outside. Two completely different physical situations, one involving the extreme gravity of a collapsed star, the other involving the large-scale stretching of the entire universe. And yet the same underlying mathematics of an event horizon governs both, producing the same strange asymptotic fading at the boundary. The universe, it turns out, only has one way of drawing a permanent line like this. And it uses that same trick at every scale, from the edge of a black hole a few miles across, to the edge of the observable cosmos, tens of billions of light-years across. Right now, based on current models of dark energy and cosmic expansion, that cosmological event horizon sits at approximately 16 billion light-years from us. Any galaxy currently beyond that distance is already, in a very real sense, gone. Any light it emits from this point forward will never reach Earth. No matter how long we wait, no matter what technology we develop, no matter how patient we are, the light that has already left those galaxies before crossing this threshold, light already in transit toward us, will still eventually arrive. But new light emitted after the crossing is lost to us permanently. And here's the detail that makes this genuinely difficult to sit with. Because of accelerating expansion, this boundary is effectively shrinking in terms of how much of the currently visible universe remains reachable in the future. More and more galaxies currently visible to us tonight are crossing that threshold as time passes. Their light is getting redder and redder, more and more stretched by the expansion of space, dimmer and dimmer, approaching a point where they will fade from view entirely and their light will simply stop arriving. We are not slowly gaining access to more of the universe. We are slowly losing access to the part we already have. Let's make this concrete because abstract numbers about billions of light years can start to blur together if we don't ground them in something specific. There are galaxies visible in deep telescope images today. Galaxies astronomers have photographed and cataloged that are currently receding from us fast enough that they have already crossed or are very close to crossing the cosmological event horizon. Their light is still arriving because it left long ago before the crossing happened. But if intelligent beings existed on a planet in one of those galaxies right now and pointed a telescope at us this very moment and sent a signal our way, that signal would never arrive. It's not that it would take a very long time. It's that it would never get here under any physical model we currently understand because the space between us would be stretching faster than that signal could ever cross it. We would be permanently physically unreachable to each other. Not because of distance in the way distance usually works, but because the very fabric separating us grows faster than anything could ever cross it. Two civilizations existing at the same cosmic moment in the same universe, utterly and permanently cut off from ever exchanging so much as a single photon of information forever. That's not a hypothetical far future scenario. Based on current models, this is already true for a significant number of galaxies observable in our sky tonight. It gets even more specific and even more strange when you consider our own galactic neighborhood. The Milky Way is part of a small cluster of galaxies called the Local Group, which includes Andromeda, the Triangulum Galaxy, and dozens of smaller dwarf galaxies, all bound together by gravity strongly enough to resist the overall expansion of the universe. Zoom out a bit farther and the Local Group is part of a larger structure called the Virgo supercluster, though the gravitational binding at that scale is much weaker. Here's the important distinction. Anything gravitationally bound to us tightly enough like Andromeda will never be carried away by cosmic expansion. No matter how much dark energy accelerates everything else, gravity locally overwhelms the stretching of space at these scales. Andromeda is actually approaching us, and in roughly 4 billion years our two galaxies are expected to collide and merge. But almost everything beyond our immediate gravitationally bound neighborhood, essentially every other galaxy cluster and supercluster in the observable universe, is not gravitationally bound to us and is subject to this ongoing accelerating separation. Over enormously long timescales, hundreds of billions of years from now, the picture of the universe from Earth, or whatever remains of Earth's location by then, will look radically different from tonight. Distant superclusters, entire structures made of thousands of galaxies, will have faded from view entirely, redshifted into darkness, their lights stretched beyond detection, their positions beyond the cosmological event horizon. Eventually, in an unimaginably distant future, calculations suggest that observers in our galactic neighborhood would see essentially nothing beyond our own gravitationally bound cluster. No other galaxies, no other superclusters, just our own local group, a handful of nearby dwarf galaxies, and the merged remains of the Milky Way and Andromeda hanging alone in an otherwise dark and silent sky. Just an increasingly dark, increasingly empty-looking universe, even though the actual universe would still be out there, unimaginably vast, simply beyond any possibility of detection. Zoom out even further for a moment to see where our own gravitationally bound neighborhood sits within the larger structure of the cosmos. Galaxies aren't scattered randomly through space. They're arranged into a vast sprawling structure sometimes called the cosmic web, made up of filaments, sheets, and clusters of galaxies, separated by enormous, mostly empty voids. Our local group sits within a larger structure called the Laniakea supercluster, a name meaning immeasurable heaven, containing roughly 100,000 galaxies spread across a region about 500 million light-years across. Within Laniakea, everything is being drawn very slowly toward a gravitational concentration called the Great Attractor, a dense region partially hidden from view behind our own galaxy's central bulge. Even farther out, entire superclusters like Laniakea are themselves part of even larger structures and separated by voids so empty that some regions contain a tiny fraction of the average density of matter found elsewhere in the universe. Mapping this structure has taken decades of painstaking observational work, and it reveals something important for our purposes tonight. Gravity organizes matter into these clusters and filaments precisely because gravity at these scales can still act faster and stronger than the stretching of space around it. Most of that gravity, it turns out, doesn't come from anything we can directly see. Ordinary matter, the atoms making up stars, planets, gas, and dust, accounts for only about 5% of the total content of the universe. Roughly 27% is something called dark matter, a form of matter that doesn't emit, absorb, or reflect light in any way we've been able to detect directly, but whose gravitational influence is unmistakable, revealed through the way it affects the rotation of galaxies, the motion of galaxy clusters, and the bending of light itself as it passes through massive concentrations of it. Without dark matter's gravitational pull, the filaments and clusters that make up the cosmic web likely wouldn't have formed at all, at least not in anything resembling their current structure. Ordinary matter alone doesn't provide enough gravitational glue to explain the large-scale organization we observe. Dark matter, whatever it actually turns out to be, provided the scaffolding that ordinary matter later collapsed into, forming the galaxies, clusters, and superclusters that now populate the cosmic web, held together against the backdrop of an otherwise ever-expanding universe. It's a strange thought that most of what's holding our own galactic neighborhood together against the pull of cosmic expansion is something we still don't fully understand or have never directly detected in a laboratory. And yet its effects are woven into every structure we've just described. But go far enough out past the edge of any supercluster into the vast connecting filaments and beyond, and the balance shifts entirely in favor of expansion. The structures we can map today, Laniakea and its neighboring superclusters, represent the practical limit of what will ever remain gravitationally connected to us. Everything else, every other filament, every other void, every other supercluster in the cosmic web, is destined to eventually cross the cosmological event horizon, one galaxy at a time, fading from view over the ages. The cosmic web we can map today is in a sense a snapshot of connections that are actively, slowly dissolving. This raises an important question, one that's genuinely debated among cosmologists, and it deserves to be addressed directly rather than glossed over. If a civilization arose in that unimaginably distant future, hundreds of billions of years from now, long after most galaxies had redshifted beyond the horizon, what would they conclude about the universe? Their observable universe would appear to contain only their own local galactic structure. They would see no cosmic microwave background since it would have redshifted into wavelengths too long to detect with any plausible instrument. They would see no distant galaxies. They might reasonably conclude based purely on their own observations that the universe was small, static, and essentially empty beyond their own neighborhood. They would be wrong, catastrophically wrong, but they would have no way of knowing it because the evidence that would correct their view would already be permanently unreachable to them. This should make you pause because it suggests something uncomfortable about our own position right now. We look out at our observable universe, 46 billion light-years in radius, filled with galaxies, and we build our entire understanding of cosmology based on what we can see within that boundary. But we now know with reasonable confidence that this is not the whole picture. There's more universe out there beyond our horizon that we will never see, never measure, never confirm. We are, in a sense, already living inside the early version of that future scenario. We just don't yet realize how much we're missing, because unlike that far future civilization, we still have access to enough of the universe to piece together the physics that tells us what we're missing. That access is not guaranteed to last forever. Here's what that far future actually looks like stage by stage. Because the timescales involved are so far beyond ordinary human experience that they need to be laid out carefully. Right now, we exist in what cosmologists call the stelliferous era, the age of stars, which began roughly a few 100 million years after the beginning of everything and is expected to continue for perhaps another 100 trillion years, as existing gas clouds are slowly used up in star formation and the smallest, longest-lived stars, the red dwarfs, burn through their fuel at an incredibly slow rate. During this era, which we are still very early in, galaxies beyond our own gravitationally bound neighborhood will continue crossing the cosmological event horizon, one after another fading from detection. After the stelliferous era ends, once the last stars flicker out, the universe enters what's sometimes called the degenerate era, dominated by burnt-out stellar remnants. White dwarfs, neutron stars, and black holes with no new star formation to speak of, stretching from roughly 100 trillion years to something on the order of 10 to the 40th power years. A number so large it stops being meaningful as anything other than an abstraction. Eventually, even those remnants decay, black holes evaporating through an extremely slow quantum process, leading into what's called the black hole era. And finally, the dark era, an unimaginably distant future dominated by nothing but the faintest trace of thinly spread particles and radiation drifting through an almost perfectly empty, almost perfectly dark universe. Throughout all of these stages, the cosmological event horizon continues doing its work, continuing to carry more and more of what once existed beyond any possibility of contact, long after there's anyone left to notice. By the time any civilization might exist in the later stages of the degenerate era, assuming any form of intelligence could persist that long, the observable universe would contain essentially nothing beyond whatever remnants happened to be gravitationally bound to it from the very beginning. The rest of the story, everything happening everywhere else in the cosmos, would already be sealed away permanently long before that point. This final picture deserves more than a passing mention given the sheer scale of it. As the degenerate era stretches on, white dwarfs, the slowly cooling embers of stars like our own sun will gradually radiate away their remaining heat over spans of time measured in the tens of billions to trillions of years, eventually cooling into cold, dark spheres called black dwarfs. Though the universe isn't yet old enough for any to have actually formed, since even the oldest white dwarfs currently known haven't had nearly enough time to cool that far. Some theoretical models predict that protons themselves, the building blocks of ordinary matter, might not be perfectly stable over timescales vastly longer than the current age of the universe, potentially decaying into lighter particles given enough time on the order of 10 to the 34th power years or longer. Though this remains unconfirmed by any direct experiment, if true, even the cold, burnt-out remnants of stars would eventually crumble away entirely, atom by atom, leaving behind nothing but a thin scattering of fundamental particles and radiation. Black holes, meanwhile, slowly evaporate through an extraordinarily gradual quantum process first described theoretically by physicist Stephen Hawking, radiating away their mass as faint radiation over spans of time that dwarf every other number mentioned tonight. A black hole, the mass of the sun requiring something on the order of 10 to the 67th power years to fully evaporate, and the largest supermassive black holes like the ones powering those ancient quasars we described earlier requiring far longer still. By the time the last black hole finally evaporates, the observable universe, whatever remains of it, would consist of nothing but an extremely thin, extremely cold haze of particles spread across a volume of space almost impossible to describe in ordinary terms, with a temperature approaching absolute zero, though never quite reaching it exactly. This is what's sometimes called the heat death of the universe. Not a dramatic ending, but a quiet, gradual fade into maximum entropy, maximum disorder, and effectively permanent stillness. The cosmological event horizon and everything it has carried beyond reach along the way would by then be an almost meaningless concept, since there would be essentially nothing left anywhere to be separated from anything else in any way that mattered. All of this rests on an assumption, and scientific honesty means acknowledging it directly. We're assuming dark energy continues behaving the way it appears to behave right now, driving a steady, accelerating expansion indefinitely into the future. That assumption might not hold. Some theoretical models propose that dark energy could be a form of what's called quintessence, a field whose strength might change over time rather than remaining constant. If dark energy weakens significantly in the future, the acceleration could slow and the cosmological event horizon could actually grow outward again over unimaginably long timescales, recovering contact with regions currently being lost. Other more unsettling models propose the opposite, something called phantom energy, where the strength of this repulsive force could actually increase over time, accelerating the expansion faster and faster without limit. In the most extreme version of this scenario, sometimes called the Big Rip, the expansion would eventually become so violent that it would tear apart galaxies, then solar systems, then planets, then eventually atoms themselves, ripping the fabric of matter apart directly. An outcome that some models place at the very earliest tens of billions of years from now. Though current evidence doesn't strongly favor this particular scenario over the simpler steady acceleration we've been describing, current measurements are consistent with dark energy behaving as a true cosmological constant, an unchanging property of empty space itself. But the precision of those measurements isn't yet good enough to completely rule out slow changes over time. This means everything we've described tonight about the shrinking bubble of what remains reachable is our best current understanding, built on solid evidence, but genuinely open to refinement as measurements improve over the coming decades. The barrier is real. Its exact future behavior, whether it continues at the same pace, slows down, or accelerates further, is one of the biggest open questions in cosmology today. Consider how confident we actually are in a number like the age of the universe, 13.8 billion years, since it underlies almost everything we've described tonight. That figure doesn't come from a single measurement or a rough estimate. It comes primarily from an extraordinarily detailed mapping of the cosmic microwave background carried out most precisely by a European Space Agency satellite called Planck, launched in 2009, which measured tiny temperature variations across that ancient light. Variations of only a few parts in 100,000 corresponding to the faint density differences that would later grow into every galaxy, every cluster, every filament in the cosmic web. By carefully analyzing the precise pattern and scale of these tiny variations, cosmologists can work backward using well-tested physics to determine the age, composition, and expansion history of the universe with remarkable precision, arriving at that 13.8 billion year figure with an uncertainty of only a small fraction of 1%. This same dataset is what pins down the roughly 5% ordinary matter, 27% dark matter, 68% dark energy breakdown we mentioned earlier. It's genuinely one of the most precise measurements in all of science, considering it's describing the entire universe. And it's the foundation underneath every distance, every horizon, and every number we've discussed tonight. There's one more piece of this puzzle, because the idea of causally disconnected regions unable to ever influence each other, isn't unique to the far future barrier we've been describing. It appears right at the very beginning, too. When cosmologists first mapped the cosmic microwave background carefully, they found something puzzling. Regions of the sky separated by enormous distances so large that given the age of the universe at the time that light was emitted, there shouldn't have been enough time for any signal, even one traveling at the speed of light, to have passed between them, nevertheless showed almost exactly the same temperature to a precision of a few parts in 100,000. How could regions that had never been in causal contact, regions separated by a distance greater than light could have crossed in the available time, end up looking so remarkably similar? This became known as the horizon problem, and it was one of the major motivations for proposing cosmic inflation in the first place, that extraordinarily rapid early expansion we mentioned earlier. The leading explanation suggests that these now widely separated regions were actually in close contact and had time to reach the same temperature through ordinary physical interaction before inflation rapidly stretched the space between them far apart, faster than light could keep up, carrying regions that were once in easy contact to positions so distant that light could no longer bridge the gap within the remaining age of the universe. In other words, our universe experienced its own miniature version of the exact barrier we've been describing tonight, right at its very beginning on a much smaller scale, when the same stretching of space outran the speed of light and separated regions that had once been able to communicate freely. The pattern we've spent this entire video exploring, expansion outrunning light, severing connection, sealing regions off from each other, isn't a strange exception happening only now in our current era of accelerating dark energy. It's something the universe has apparently done before, right at the dawn of everything, and something it continues doing today and will likely keep doing for the rest of its existence. Let's step back for a moment and address something that naturally comes up once you understand all of this. Couldn't we just travel fast enough to catch up with distant galaxies before they cross the horizon? Couldn't a sufficiently advanced civilization, given enough time and sufficiently powerful propulsion, chase down galaxies and establish contact before they're lost? The honest answer, based on our current understanding of physics, is no. And the reason is the same reason light itself can't do it. Nothing with mass can travel at the speed of light, let alone faster. Even a spacecraft traveling at close to light speed, something far beyond any technology that currently exists or is currently even theorized as physically achievable, would still be limited by the same speed constraint that light is limited by. If light emitted from a galaxy today will never reach us because of the stretching of space, then a spacecraft traveling at any speed less than or equal to light speed, launched from Earth today chasing that same galaxy, would face exactly the same problem and likely a worse one, since light has a head start and no mass to slow it down. There is no clever engineering solution to this. There is no propulsion breakthrough that fixes it. This isn't a limitation of current rocket technology. It's a geometric fact about how space itself behaves, baked into the structure of the cosmos. One clever-seeming loophole comes up often, and it's a genuinely reasonable question rooted in real physics. Einstein's theory of relativity tells us that time itself passes more slowly for an object moving close to the speed of light relative to an observer who stays still. This is called time dilation, and it's not a theoretical curiosity. It's measured routinely in particle accelerators and even in slight, precisely measured differences between atomic clocks flown on aircraft versus clocks left on the ground. A traveler moving fast enough, close enough to the speed of light, could in principle experience a journey of tens of thousands of light years as lasting only a few subjective years from their own point of view, even though far more time would pass back on Earth. This effect is real, and it's often brought up as a potential way to shrink the practical difficulty of interstellar or even intergalactic travel from the traveler's own perspective. But it doesn't help with the barrier we're describing tonight, and understanding why reveals something important about the difference between subjective experience and physical possibility. Time dilation changes how much subjective time a traveler experiences during a journey. It does not change the physical distance being crossed or the fact that a traveler still cannot exceed the speed of light relative to the space they're moving through. A galaxy beyond the cosmological event horizon is receding faster than light, meaning the physical distance between here and there is growing faster than anything, including a traveler experiencing heavily dilated time, could ever cross it. No matter how slow the traveler's clock ticks from their own point of view, they still cannot outrun the stretching of space itself. Time dilation could shrink the subjective experience of crossing our own reachable universe dramatically, making journeys of tens of thousands of years feel to the traveler like a handful of years. But it offers no help whatsoever in reaching anything beyond the point where recession velocity already exceeds the speed of light. The barrier isn't about how much time a journey takes. It's about whether the destination is getting closer or farther away faster than anything can travel toward it. And no amount of clever relativistic time management changes that basic geometric fact. Beyond the cosmological event horizon, contact isn't difficult. It's not a matter of degree requiring only more energy or cleverness. It is, based on everything we currently understand about physics, categorically, permanently impossible. There's a subtlety here that's often misunderstood even by people who follow astronomy closely. The cosmological event horizon we've been describing is specific to our location in the universe. Every observer everywhere in the cosmos has their own version of this horizon centered on themselves. A civilization on a planet 10 billion light-years from here would have a different observable universe and a different cosmological event horizon centered on their own position. There's no special privileged center to any of this. The universe doesn't revolve around Earth in any physical sense. Every point in the universe experiences itself as the center of its own observable bubble, surrounded by its own version of this receding barrier. This is deeply consistent with everything we understand about the large-scale structure of the cosmos, which appears as far as we can measure to be roughly the same in every direction and from every vantage point, a principle cosmologists call the cosmological principle. It means the barrier isn't something unique to us or something imposed on us specifically. It's a universal feature of any observer existing inside an accelerating, expanding universe like ours. There's a genuinely strange symmetry buried in this idea. Somewhere right now beyond our own cosmological event horizon, there could be an observer on some world we will never see, looking out at their own sky, watching their own galaxies fade at the edges of their own bubble. From where they stand, our own galaxy, the Milky Way, sits just as thoroughly beyond their reach as their galaxy sits beyond ours. Neither of us is at the true center of anything, and neither of us occupies a more privileged vantage point than the other. We are simply two observers, each sealed inside our own expanding bubble, each perfectly correct in describing our own observable universe as vast and complete, and each entirely unaware of the other's existence permanently, symmetrically, forever. This is perhaps the clearest way to understand that there's nothing special about our position causing this barrier. It's not that we happen to be unlucky or poorly located. Every single point in the universe experiences exactly the same boundary at exactly the same underlying distance, shaped by exactly the same physics. An infinite number of bubbles, overlapping and interlocking across the cosmos, each one someone's entire observable reality, each one permanently mutually sealed off from almost every other one. Every civilization everywhere wrapped in its own bubble, permanently, isolated from almost everything else, whether they realize it or not. This actually offers a quiet partial answer to a question you may have heard before, sometimes called the Fermi paradox, which asks why, given the sheer number of stars and potentially habitable planets in our galaxy alone, we haven't detected any clear signal from another intelligent civilization. There are many proposed explanations for this silence, ranging from the rarity of life itself to the difficulty of intelligence evolving at all to civilizations destroying themselves before developing the technology to communicate across interstellar distances. The barrier we're describing tonight adds another layer to that conversation, though it mostly applies at a much larger scale than the Fermi paradox usually concerns itself with. Even if the universe were teeming with intelligent civilizations, evenly scattered across every galaxy, a significant number of them would already exist beyond our cosmological event horizon, permanently incapable of ever exchanging a signal with us, simply due to the accelerating stretch of space between us and them. The silence we observe isn't just about distance in the ordinary sense, the kind that a powerful enough radio telescope might eventually overcome. Some of that silence is built into the structure of space-time itself, guaranteed, permanent, and completely independent of how advanced anyone's technology becomes. We were never going to hear from those civilizations, not because they aren't out there, but because the universe itself has already ruled out the possibility of the conversation ever happening. Actual searches for extraterrestrial signals show just how enormous our own galaxy is, long before the cosmological event horizon becomes relevant at all. Organized efforts to search for artificial radio signals from other civilizations have been ongoing since the 1960s, scanning nearby stars for any transmission that couldn't be explained by natural astrophysical processes. To date, no confirmed signal of artificial origin has ever been detected. But even a thorough, sustained search focused entirely on our own galaxy is really only sampling an infinitesimally small fraction of the roughly 100 billion stars within the Milky Way, let alone anything beyond it. Any hypothetical signal would also need to have been transmitted and aimed roughly in our direction during the narrow window of time when both civilizations happen to exist with compatible technology. A coincidence of timing that becomes less and less likely the more you think through it carefully. Even setting aside the cosmological event horizon entirely, simply finding another civilization within our own reachable galaxy is already an extraordinarily difficult problem of scale, timing, and detection sensitivity. The event horizon we've described tonight simply adds an outer limit to that search, guaranteeing that no matter how sensitive our instruments eventually become, no matter how long we search, a significant portion of any civilizations that might exist across the wider universe were never within the realm of possible contact in the first place. Let's talk about scale for a moment because the numbers involved are staggering. Current estimates suggest the observable universe contains somewhere on the order of 2 trillion galaxies. That figure has actually been revised downward and upward multiple times over the past decade as telescope resolution improved, with some earlier estimates running even higher. But 2 trillion remains a commonly cited figure from deep field surveys. Each of those galaxies contains on average somewhere between 100 billion and several hundred billion stars. Multiply those two numbers together and you get a rough total star count for the observable universe alone, somewhere in the range of 1 followed by 24 zeros. A number so large it stops functioning as a quantity and starts functioning more like an abstraction. The sheer scale of this is already almost impossible to hold in your mind clearly. But remember, this is only the observable universe, the portion within our current cosmic horizon. Whatever exists beyond the cosmological event horizon, permanently unreachable to us, could easily dwarf this number. Some theoretical models based on the physics of cosmic inflation in the earliest fractions of a second after the beginning of everything suggest the total universe, including everything beyond what we can ever observe, could be many orders of magnitude larger than the observable portion, possibly even infinite in extent. We simply have no way to confirm this directly, and likely never will, precisely because of the barrier we've spent this entire video describing. We are sealed inside a knowable region embedded within something almost certainly far larger. And that larger region is by definition permanently beyond our reach. There's an even more extreme version of this idea, one that sits at the very edge of accepted physics, and it takes the concept of a hidden barrier to its most extreme possible conclusion. Some models of cosmic inflation, the extraordinarily rapid expansion thought to have occurred in the tiniest fraction of a second after the beginning of everything, suggest that inflation might not have happened everywhere uniformly and might not have even stopped everywhere at the same time. In these models, sometimes called eternal inflation, our entire observable universe, everything we've been describing tonight, the 2 trillion galaxies, the 46 billion light-year sphere, all of it, might be just one bubble among countless other bubbles, each one forming its own separate region, each one potentially governed by different physical constants, different laws, different versions of physics entirely. If this picture is correct, then the cosmological event horizon we've spent this video describing is really just the innermost of several nested barriers. Beyond it lies the rest of our own universe, permanently unreachable. And beyond that, in these models, could lie an uncountable number of entirely separate universes, each with their own equivalent horizon, each just as permanently sealed off from ours as the most distant galaxy in our own universe is sealed off from us. This idea remains genuinely speculative, difficult to test directly, and far from settled science, unlike everything else described tonight, which rests on solid observational evidence. But it illustrates just how deep this pattern of hidden barriers might actually run. Layer after layer, each one just as absolute as the last, each one just as invisible until you understand the physics that reveals it. A handful of researchers have even proposed that if these other bubble universes exist, and if one happened to have formed close enough to ours in whatever higher dimensional space contains all of them, a collision between two bubbles early in cosmic history might have left behind a subtle detectable imprint on our own cosmic microwave background, a slightly cooler or warmer patch distorted in a specific predictable way. A few unusual, statistically debated features have actually been reported in detailed CMB maps over the years, including an unusually cold large region sometimes called the CMB cold spot, and various proposed explanations for it have included exactly this kind of bubble collision scenario, alongside far more mundane explanations involving ordinary foreground structures or simple statistical flukes. No such claim has been confirmed to the standard of evidence required for genuine scientific consensus, and most cosmologists remain appropriately skeptical, treating it as an interesting anomaly worth further study rather than confirmed evidence of anything beyond our own universe. But it's a striking thought regardless that the same instrument revealing the oldest light in our own universe, the cosmic microwave background, might just possibly also contain a faint, ancient bruise left behind by a glancing encounter with a universe entirely separate from our own, sometime in the earliest fractions of a second after everything began. If true, it would mean the barrier separating universes isn't quite as absolute as the barrier separating galaxies within our own universe, since a genuine physical trace might have crossed it once, however faintly, in a way ordinary light and matter never could again. This touches on the limits of scientific knowledge itself, not just the limits of technology. Science generally works by gathering evidence, testing predictions, and refining our understanding based on what we observe. But what happens when the thing you want to understand is structurally, permanently unobservable? Cosmologists deal with this problem constantly when discussing what lies beyond the cosmological event horizon. We can make mathematically consistent extrapolations based on the physics we do understand within our observable region, assuming those same physical laws hold true everywhere. That assumption is reasonable, and it's supported by everything we've measured so far, since the observable universe appears remarkably uniform in its fundamental physics from every direction we look. But it remains an assumption, not a direct observation, when applied to the region beyond our horizon. This is one of the genuine, humbling limits of cosmology as a science. Not every mystery is one we're simply waiting to solve with a bigger telescope or a cleverer experiment. Some mysteries are built into the structure of what can ever be known by any observer in this particular kind of universe, no matter how long that observer waits or how advanced their instruments become. Now, let's connect this back to something more personal, because it's easy to let all of this stay abstract, floating somewhere out among galaxies billions of light years away. Consider what this barrier means for the practical future of any civilization, including our own, that might dream of expanding outward into the universe. Even setting aside the cosmological event horizon entirely, even just considering ordinary interstellar distances within our own galaxy, the challenges are already enormous. The nearest star system to our own, Alpha Centauri, sits about 4.37 light-years away, at the speed of the fastest spacecraft humanity has ever built. Reaching even that comparatively close destination would take tens of thousands of years. To put that in perspective with something we've actually launched, Voyager 1, launched in 1977 and now the most distant human-made object in existence, travels at roughly 38,000 miles per hour. And even at that considerable speed, it would take Voyager 1 over 70,000 years to cover the distance to Alpha Centauri if it happened to be traveling in that direction at all, which it isn't. Here is the text from the video, rewritten to remove the timestamps and flow as a continuous narrative, picking up from where the previous response left off. Proposed future concepts like small probes accelerated by powerful ground-based lasers pushing against lightweight sails have been theorized as potentially reaching a meaningful fraction of light speed, perhaps 20% of it, which would cut a journey to Alpha Centauri down to roughly 20 years rather than tens of thousands. Even that remains purely theoretical, requiring engineering far beyond anything currently demonstrated, and it would only work for extremely small, lightweight probes, not for anything resembling a crewed spacecraft or a colony ship. For an actual crewed mission to another star system using any propulsion technology currently understood as physically plausible, the journey would likely take centuries at minimum, leading to serious proposals over the decades for what are sometimes called generation ships. Enormous self-sustaining vessels designed to support multiple generations of travelers born, living, and passing on aboard the ship itself, with only their distant descendants ever setting foot on the destination world. Other proposals lean towards suspended biological states, slowing human metabolism dramatically for the duration of the journey, or toward transmitting digital representations of human minds to be reconstructed at the destination, sidestepping the biological challenges of a multi-century voyage entirely, though this remains firmly in the realm of speculation rather than anything close to demonstrated technology. Some longer-term proposals imagine civilizations eventually constructing enormous structures called Dyson swarms, vast collections of solar collectors surrounding an entire star to capture nearly all of its energy output, potentially providing enough power to support extraordinarily ambitious projects, including sustained interstellar expansion across many nearby star systems over tens of thousands of years. Now consider that the entire observable universe, the vast majority of which we can only ever observe passively and never actually visit, extends across a distance so large that light itself takes tens of billions of years to traverse comparable spans. Any civilization dreaming of expanding to fill the universe, colonizing distant galaxies, spreading life and intelligence across the cosmos, runs directly into two separate compounding barriers. The first is simply the practical difficulty of traveling vast interstellar and intergalactic distances with anything resembling currently understood propulsion technology. The second, far more fundamental, is that a meaningful fraction of the galaxies we can currently see are already receding fast enough that no form of travel at any speed up to and including the speed of light could ever reach them, because the space between us and them is stretching faster than any traveler could cross it. There is no version of the future under our current understanding of physics in which humanity or any civilization anywhere spreads across the entire universe. Not eventually, not with better technology, not with more time. The universe itself, through the geometry of its own expansion, has already ruled that out for a large and growing portion of what exists. Something here might feel discouraging because it's easy for this kind of information to land as bleak, even though that's not really the right way to think about it. The existence of this barrier doesn't diminish what's actually reachable. Within our own galaxy alone, the Milky Way contains somewhere around 100 billion stars, many with planetary systems of their own, spread across a disk roughly 100,000 light-years in diameter. Even limiting any future exploration entirely to our own galaxy, gravitationally bound and in no danger of ever crossing any cosmic horizon, represents an almost unimaginable scope of potential discovery, far beyond anything a species could exhaust in any reasonable span of time. Consider what we've already found just in our own galactic backyard. Since the first confirmed detection of a planet orbiting another sun in the 1990s, astronomers have confirmed the existence of more than 6,000 exoplanets with thousands more candidates awaiting confirmation. And that count comes from surveying only a tiny fraction of the roughly 100 billion stars believed to exist within the Milky Way alone. Statistical extrapolation from these surveys suggests that planets are common around stars generally, meaning our own galaxy likely contains billions of planets, an unknown but potentially substantial fraction of which could sit within the habitable range of temperatures where liquid water might exist on their surface. That's an entire galaxy's worth of potential destinations, potential discoveries, potential mysteries, all of it entirely reachable in principle, unlike the vast majority of the 2 trillion galaxies making up the wider observable universe. None of it requires crossing any horizon, cosmological or otherwise, just time, curiosity, and better engineering than we currently have. The barrier we've been discussing tonight matters more as a statement about the ultimate scale and structure of the universe and the humility it demands of us than as a practical limitation on anything achievable in the coming centuries or millennia. We are not running out of universe to explore. We are simply learning that the universe in its totality was never fully ours to reach in the first place, and that most of it never will be, no matter what we do. That's a very different kind of limitation than running out of room nearby. There's one more layer to this, and it reframes the entire idea in a way that connects back to where we started with the ocean horizon on the beach. Remember that the ocean horizon isn't a real boundary. It's a limitation of your vantage point, and it moves if you change your vantage point by climbing higher or moving to a different location. The cosmological event horizon is different in a crucial way. It isn't caused by your vantage point in any comparable sense. Moving to a different location in the universe doesn't let you see farther in any meaningful way that changes the fundamental picture, because every location has its own equivalent horizon at roughly the same distance, shaped by the same underlying physics of accelerating expansion. There's no hill to climb that reveals more of the true total universe. There's no vantage point advantage available to any observer anywhere. This is what makes it different from every other kind of horizon or limitation humans have encountered throughout history. Sailors once thought the ocean horizon marked the edge of the world, until ships proved that wrong by sailing over it and coming back with reports of more world beyond. There's a more direct historical parallel, and it involves the exact same object we mentioned earlier, the Andromeda Galaxy. For most of the 1800s and into the early 1900s, astronomers debated what these faint fuzzy patches of light scattered across the sky called nebulae actually were. One camp believed they were relatively small, nearby clouds of gas entirely contained within our own galaxy, which at the time many assumed represented the entire universe in its totality. The philosopher Immanuel Kant had actually proposed back in the 1700s that some of these nebulae might be entire separate galaxies, island universes in their own right, far beyond our own. But it took until 1920 for the debate to reach a formal public head in what became known as the Great Debate, held at the Smithsonian between astronomers Harlow Shapley and Heber Curtis, arguing opposing sides of exactly this question. It was Edwin Hubble just a few years later, using the largest telescope in the world at the time, who settled the matter conclusively by identifying a specific type of star called a Cepheid variable within the Andromeda Nebula and using its known brightness pattern to calculate its true distance. The answer was staggering for the time. Andromeda wasn't a nearby gas cloud at all. It was an entire separate galaxy, comparable in size to our own, sitting roughly 2.5 million light-years away, far beyond anything anyone had previously imagined our galaxy's boundary to represent. Overnight, the known universe expanded from a single galaxy to an uncountable multitude of them. This is exactly the pattern we mentioned. Early astronomers once thought the visible stars marked the edge of the universe, until better telescopes revealed galaxy after galaxy stretching far beyond what earlier instruments could detect. Every previous horizon in human history turned out to be a limitation of instruments or vantage point, eventually overcome by better tools or bolder journeys. This one is different. This one is built into the geometry of spacetime itself. And there is no tool, no journey, no vantage point that gets around it. It's the first horizon we've ever encountered that we can prove mathematically, using well-established and thoroughly tested physics, is permanent. Let's take a moment to appreciate just how recently we figured all of this out, because it puts our current understanding in a useful perspective. The idea that the universe was expanding at all wasn't established until Hubble's observations in the 1920s. The discovery that this expansion is accelerating didn't come until 1998, work that was later recognized with a share of the 2011 Nobel Prize in Physics. That means humanity has known about the accelerating nature of cosmic expansion, and therefore about the true permanent nature of this cosmological horizon, for less than 3 decades. For nearly the entire history of astronomy, going back thousands of years, humans looked at the night sky and simply assumed that given enough time and enough technology, everything up there was theoretically reachable or at least observable eventually. We now know that assumption was wrong, and we've known it for a genuinely short amount of time relative to how long humans have been looking up and wondering. This is still an active, evolving area of research. The precise value of the Hubble constant is still being refined, with different measurement techniques giving slightly different results. A discrepancy cosmologists call the Hubble tension, which remains unresolved. The exact nature of dark energy remains completely unknown. Whether the acceleration of expansion is constant, increasing, or even eventually reversing remains an open theoretical question, though current evidence favors continued acceleration. Everything described tonight represents our best current understanding built on solid, repeatedly confirmed observations. But cosmology is a field still actively refining its picture of exactly how this barrier behaves over the deepest stretches of time. Let's bring this together with one final concrete way of thinking about it. Because after all these numbers and concepts, it helps to end with something clear and direct. Imagine the entire universe as an ocean, infinitely larger than any ocean on Earth, filled with islands. Each island a galaxy, each galaxy filled with countless smaller lights, each light a star. You are standing on one particular island in one particular corner of that ocean looking out. You can see other islands nearby clearly in sharp detail. You can see islands farther out, dimmer, hazier, their details harder to make out. And far in the distance, at the very edge of what your eyes can detect, there are islands so faint you can barely tell they're there at all. Their light, almost swallowed by the sheer distance it had to travel to reach you. Now imagine that this entire ocean is slowly, invisibly growing wider every single moment, faster and faster as time goes on, stretching the distance between every island and every other island, including your own. The distant islands, the faint ones at the edge of your vision, are being carried away faster than their own light can travel toward you. One by one, silently, without any dramatic event marking the moment, their light stops arriving. They fade imperceptibly at first, then more noticeably until eventually they vanish from view entirely, even though the islands themselves are still out there, still standing, simply no longer visible from where you stand. Even before a galaxy fully vanishes, its light changes in a way you could notice if you watched carefully over a long enough span of time. Its color shifts redder and redder as the space between you and it stretches more and more. Its light grows dimmer, spread out over an ever-growing area as the distance increases. And strangely, any regular repeating event happening within that galaxy, the flickering of a variable star, the orbit of a companion object, would appear to you to slow down, stretched out in time, the same way the light's wavelength is stretched out in color, a direct consequence of the same expansion doing both things simultaneously. You will never sail to them. You will never even see them clearly again. And this is happening right now to real galaxies in the real universe as you listen to this. So here is the honest, complete picture laid out plainly. The universe you can currently observe spans roughly 46 billion light-years in every direction, containing an estimated 2 trillion galaxies, an almost incomprehensible amount of matter, light, and structure. But beyond that, and growing beyond that every single day, sits a permanent physical barrier, the cosmological event horizon, currently around 16 billion light-years away, beyond which nothing that happens will ever be knowable to us, and nothing we do will ever be knowable to whatever or whoever exists there. This barrier isn't a failure of our telescopes. It isn't something better technology will eventually overcome. It's a direct, unavoidable consequence of the accelerating expansion of space itself. A feature baked into the fundamental geometry of the cosmos we happen to live in. We are not looking out at the whole universe. We are looking out at a bubble. Our bubble slowly shrinking in terms of how much of what we currently see will remain reachable in the deep future, surrounded on all sides by a boundary we can calculate with precision, but never under any circumstances cross. Name exactly what stays inside that bubble with us, and the boundary settles into its proper place rather than feeling like the whole story. Every star you can see with your own eyes on a clear night belongs to our own galaxy, gravitationally bound, in no danger of ever crossing any horizon. That's true of every constellation you've ever learned to recognize, every star sailors once navigated by, every star ancient civilizations built calendars and myths around. Every planet, every moon, every asteroid ever visited by any spacecraft humanity has launched sits well within that same safe, permanent neighborhood. Andromeda, already falling toward us rather than away, will still be there in 4 billion years, closer than ever, filling more of the night sky by then than any galaxy does today. The barrier concerns almost everything beyond that neighborhood, the overwhelming majority of the universe's contents, but it leaves untouched the part of the cosmos we actually call home, the part any of us could ever realistically hope to explore. This isn't meant to feel small or defeating. It's meant to feel honest, because understanding the true scale and structure of the universe, including its limits, including the parts of it permanently sealed away from us, is part of actually understanding where we stand in the cosmos, rather than simply assuming everything up there is ours for the taking given enough time. We live inside an almost unimaginably vast, rich, structured universe filled with more galaxies, more stars, more potential worlds than we could explore in any conceivable span of time, even limiting ourselves entirely to what's reachable. That richness doesn't disappear because of a horizon we can't cross. If anything, it becomes more precious knowing that what we can see, what we can study, what we can someday perhaps visit, however limited compared to the true total universe, is still extraordinary, still worth every bit of curiosity we bring to it. It helps to place all of this on a single compressed timeline, the kind sometimes called a cosmic calendar, squeezing the entire 13.8 billion year history of the universe into a single imaginary year. On this scale, the beginning of everything happens at the first instant of January the 1st. The Milky Way begins forming sometime in March. The Sun and Earth don't form until early September. The first simple life on Earth appears around late September. Complex multicellular life doesn't appear until mid-December. Dinosaurs arrive around December the 26th and disappear the following day. Modern humans, our own species, appear in the final half hour before midnight on December the 31st. Every single human civilization, every war, every empire, every book ever written, occupies only the last few seconds before the calendar year ends. The accelerating expansion of dark energy, the force actively building the barrier we've spent this entire video describing, only became the dominant influence on the universe sometime in the final week of that imaginary December. Meaning the barrier itself, in cosmic terms, is an extremely recent development, arriving only after nearly the entire history of the universe had already played out. We are living through the early stages of something the universe only recently started doing. A closing of doors that will continue slowly for the rest of whatever comes next. The barrier reminds us that we exist inside something larger than we can ever fully know, larger than we can ever fully map, larger than any civilization, however advanced, could ever completely explore. There's something steadying in that rather than something to mourn. We are small in a universe defined partly by what we'll never reach. But what we can reach, what we can see, what we can understand, remains vast beyond any human timescale. And that's more than enough to spend a lifetime or a civilization exploring. So the next time you look up at the night sky, remember what you're actually seeing. Ancient light arriving from the past. Some of it from sources already carried beyond any possibility of contact by the relentless stretching of space itself. A visible universe that is not the whole universe, bounded by a horizon that isn't an illusion of distance but a genuine, permanent physical edge to what can ever be known from where you're standing. Somewhere out there right now, entire galaxies, entire civilizations perhaps, exist on the other side of a line that neither they nor we will ever cross. Not with any ship, not with any signal, not with any amount of time. The universe is not only vast, it is in a very real sense quietly closing certain doors behind it forever as it continues to expand. And that is the hidden barrier between us and the rest of the universe. Not a wall we could ever see directly, not a line drawn anywhere in space, just the simple, unstoppable stretching of the cosmos itself, carrying most of what exists forever beyond our reach. Thank you for joining me on this journey through the true edges of the observable universe. If you found this exploration valuable, a like or subscribe helps us continue making these deep examinations of the cosmos. And remember, everything we can see, everything within our reach, however small a fraction of the true universe it might be, is still more than enough to fill 1,000 lifetimes of wonder. There's still an entire galaxy of stars, planets, and mysteries sitting well within our grasp, gravitationally bound, going nowhere, waiting for exactly the kind of curiosity you brought to this video tonight. Somewhere out there tonight, a star you've never noticed is finishing a journey of light that began before your grandparents were born, arriving at your eyes as the very last thing it will ever tell you before the space between you and it stretches just a little too far forever. Good night, and may you never look at the stars the same way again, knowing that some of that light is the last message you will ever receive from places already gone beyond reach forever. Never,